This problem here exercises an isentropic compressor. We're going to be looking for the work in this instance. So here we have the temperature and pressure at the inlet, and then we have the pressure at the exit. We have no heat transfer in this case, and we're told the efficiency of this compressor, the isentropic efficiency, is 90.3%. And we're looking for the work, once again, in kilojoules per kilogram. So when you're told that you're looking for the work, what you're actually looking for is going to be called the actual work. So there's two kinds of work. So there's isentropic work and then there's actual work. Basically, the difference is that actual work is what you see from a compressor or a turbine in real life, and isentropic work would be if there was no entropy. So for example, if everything was frictionless, if you saw no power loss, and that's kind of non-existent. But to find actual work of a compressor, if you just use the first law of thermodynamics, you'll have that 0 equals the heat transfer minus the power or work, plus the mass flow rate times the inlet enthalpy minus the exit enthalpy. And we have no heat transfer. We can move the work over the other side, and we're going to have that the work equals the mass flow rate times the change in enthalpy, but we're going to divide by m because we're looking for the work on a per unit mass basis. So we'll have W over m equals H1 minus H2. Now you've probably seen a very similar expression to this, where you have the work of the compressor equals H2 minus H1. Now, the reason why you have that expression is because when you're using the first law of thermodynamics, you actually have negative work on a compressor. So when you solve for W in the first law of thermodynamics, you're going to have that WC equals H2 minus H1. But I'm just going to stick with this equation here, and it will give us a negative number. If you decide to use H2 minus H1, you'll have a positive number, but remember that compressors consume power, so it's truly work going into the compressor. But anyways, now we need to find our enthalpies. So at T1 we have 290 Kelvin. We turn to our property table for air, which is A22. We go to 290 Kelvin and you have 290.16 kilojoules per kilogram. And now we need to find T2 in order to find H2. So we're going to use the isentropic relation over this compressor. So when we have an isentropic process, we have T2 over T1 equals P2 over P1, and that's all to the K minus 1 divided by K. And now if you just rearrange and solve for T2, you'll have T1 times P2 over P1 to the K minus 1 over K. Now let's plug in what we have. So for T1, we had 290 Kelvin, and P2, we have 330 kPa, P1 was 100 kPa. Divide that, and you have a K value, K equals 1.4 for air. So now we have 1.4 minus 1 divided by 1.4. And if you plug this into your calculator, you'll have that T2 equals 407.89 Kelvin. Now, one thing you need to make note of, though, is that because we're using an isentropic relation here, this number here, 407.89, is actually going to yield you in T2S, because that's the isentropic temperature if there were no irreversibilities and this was an isentropic process. But because it's not actually an isentropic process, we're going to have to use this number to find our isentropic enthalpy, or our ideal enthalpy if there were no reversibilities. So let's go ahead and do that now. So at our ideal outlet temperature of 407.89 Kelvin, we have 400 and 410 on the property table to choose from. So it'll be somewhere between these two numbers right here. And if you just use some linear interpolation, you'll have the H2S, we'll call it H2S, the isentropic enthalpy at the exit, equals 408.98 kilojoules per kilogram. And once again, that's ideal enthalpy at the exit. You're not going to actually see that in real life because we have irreversibilities such as friction in a compressor. Now with H1 and H2S, you can find the ideal work. So for the ideal work, we have W divided by M, and it's once again isentropic or ideal. You'll have that equal to H1 minus H2S. Now there's a difference between W over M actual and W over M isentropic. One is actual work and one is isentropic work. The actual work is basically going to be the isentropic work, so we'll have W over MS divided by the efficiency of the compressor. And this equation is valid for compressors. Turbines have a different equation. But now if you notice here, we have W over M actual equals H1 minus H2, and W over MS equals H1 minus H2S, and we're already given the isentropic efficiency, so we can do some plugins here, or should I say substitutions, and you'll have H1 minus H2 equals H1 minus H2S over the isentropic efficiency. Now I did some simple rearrangements to find H2 because we're going to need H2 in order to find the actual work. So now we can plug in what we have here. So we have negative H1. H1 was 290.16. So we have negative 290.16 plus H2S, which is 408.98 kilojoules per kilogram. Divide that by the isentropic efficiency, which doesn't hold a unit, but it's going to be 0.903, which is 90.3%. And we're going to add H1, which once again is 290.16 kilojoules per kilogram. And now if you plug this into your calculator, you'll have that H2 equals 421.74 kilojoules per kilogram. So now we can go back to our initial work equation here. We have H1 minus H2, which is going to yield us with 290.16 minus 421.74, of course, kilojoules per kilogram. And if you plug that into your calculator, you'll have negative 131.58 kilojoules per kilogram. And that is your work. Now, I prefer that we came out with a negative number at the end because you have H1 minus H2. If you use H2 minus H1, you'll just have this as a positive number. But like I said, remember that you have to know that it goes into the compressor, not out of the compressor. Also, if you didn't feel like solving for H2, you can just use this expression here, which just says that the actual work equals the isentropic work divided by the efficiency. And if you just plug in your numbers here, you're going to have the H1 minus H2S, which is 290.16 minus 408.98, and divide that by 0.903. That'll also yield you with negative 131.58 kilojoules per kilogram. So you can do it either way.